A car accelerates away from a stop sign. What is the main external force on the car which provides the unbalanced forward net force on the car which causes it to accelerate? Notice you're running out of time there, so that's what I was looking for. 58% of you. It's not a kinetic friction. So we're going to talk a lot about what's called rolling without slipping. But my idea is that somehow, as this wheel is going along the carpet, the bottom, the point right at the very bottom is kind of locked in, and it's not really sliding. So I think of kinetic friction as being sliding friction, which would be kind of like this, which is not what your car is doing. Okay, I think your car is always rolling without slipping, so it's always static friction. Let me come back to this because it is a pretty difficult concept. You're sitting in your car, you step on the gas. So the car accelerates forward, to the right in this case, and there's an acceleration here. So what's the direction of the force of friction on the front wheels? And what I've said here is that your car has front-wheel drive, meaning that the engine is connected to the front wheels, and it's causing them to rotate. Like if you lifted the whole car up, the back two wheels would just stay without rotating. If you step on the gas, this would go and start spinning like that. But that's not what's happening. It's on the ground, and you're not screeching. There's no skidding. So what's the force of static friction of the road upon the front wheels? Forward, backward, or static friction is zero. So everybody says that it's a forward, so it's actually the whole thing that gets the car going, so it is important that it's forward. In this case, what is the direction of static friction on the bottom of the back two wheels? So I like B. If you've got a car and the front wheels are connected to the axle and it wants to accelerate, then the torque causes it to spin clockwise. The bottom doesn't want to go screech. So to prevent that backward screeching, there's a forward force of static friction, and that's what propels the whole car. Okay, so the back wheels are connected to the axle. They're kind of being dragged along, like if you were to pull a wagon or something. So what I like to think is that if they weren't rotating, like John's marble, then it would just slide without rolling. It would go screech along in the forward direction. So there's got to be some backward static friction force, which causes the back wheel to spin, to roll. So what I would say here is that the axle is connected to the car. The rear wheels do rotate. They don't just screech along. So why do they rotate as the car accelerates? It's not the engine that's causing them to rotate, because the engine's not connected. So why? I think that this is due to a small backward static friction force. It can't be very large or else it would slow the car down too much. It's just enough to spin those back wheels. Backward static friction force from the road. Okay? It's just enough to spin the wheel, not enough to slow down the car. So on the front two wheels, there's two very, very, very large forward static friction forces, which are propelling the whole car. And on the back two wheels, there's two very small backward static friction forces, which spin those back wheels and let them not screech along. So the situation is, I've got a horizontal flat table that John has bubble leveled, so that there's no rolling on it. And then this is going to be a top view with this GoPro down on the track. And the track is 3/4 of a circular path, and there's these walls which keep a ball on a circular path as it goes around it. So try to make a prediction. The ball rolls clockwise and then emerges onto the flat horizontal frictionless table, and you're looking down from above. Which dashed line shows the motion of the ball? Okay. Should we try it? Okay. I don't know if you believe me, but it seems to me, and I guess if we go this way as well, as soon as you take away the force that's pushing it towards the center of the circle, it just goes off in a straight line. Whatever its tangential velocity was at the moment that the force is released, that remains its tangential velocity. So it's C. The car is traveling east at a constant speed of 100 kilometers per hour. Without speeding up or slowing down, it is turning. If you can imagine, you've got your steering wheel turned left, but your cruise control is set on 100 kilometers an hour, so you're not speeding up, not slowing down. What is the direction of the acceleration? Is it A, north, B, east, C, some diagonal east of north, D, a diagonal west of north, or E is trick question, the acceleration 0 doesn't have a direction. Survey says a lot of people are saying north, and that's as simple as it is. So you are always, if you're turning at a constant speed, that acceleration vector, it means it doesn't have any parallel component to your velocity. It's only got a perpendicular component. And so whatever your velocity is, in this case, your velocity is east, then your acceleration must be either north or south if you're not speeding up or slowing down. Okay? Because if you were speeding up or slowing down, you'd have a component of the acceleration in that north or south direction. So, and then to choose whether it's you're going east. So if you're speeding up, there would be a component of your acceleration in the east direction. If you were slowing down, there'd be a component of your acceleration in the west direction. Since you're constant speed, it must be either north or south. In this case, it's north because that's towards the center of this. If you imagine this was some big circle, it kind of goes off the screen there. The center of that circular path would be to the north. You're in a plane which is accelerating forward on a runway. Some careless person has left a tennis ball in the aisle. And so just as the plane's about to take off, you notice the tennis ball rolling towards the back of the plane. So it's accelerating towards the back of the plane. So I would say that according to Newton's second law, if the acceleration is towards the back of the plane, there must be a force, net force on the tennis ball in the direction of acceleration. So what's the source of this backward net force, mostly? Is it A, air resistance, B, the plane must be at an angle, so some component of gravity provides it, D, the inertial force, C, the inertial force, D, the normal force, and E, Newton's second law is not valid in your reference frame. Ooh, 57% of you just said that Newton's second law is not valid in your reference frame. There was also a lot of votes for the inertial force. It's not air resistance because it's inside the plane. And I would say that that's not true if it's on the flat. So I would just say this is not a term we use. I put it on there as kind of a distractor. I think the best way for Physics 131 to explain this is to say that maybe the ball is, if there's no friction force on it, then as seen from the airport view, the ground view, the ball just sits there and the plane zips out forward underneath it. And you're on the plane, so you see the ball moving backwards, but it's really not moving at all. A ball is whirled in a string in a vertical circle, so I'm going to do that with this orange ball now. I don't know which way it's going. Let's just say it's going this way. So there's all these different points of motion. There's at the very bottom, point C. There's point B. Point B. A, B, C, and D. And these 4 different points. And you can think about how the tension will vary as it's going in a vertical circle. So the question is the tension either greatest at the top of the motion, A, it's constant, greatest at the bottom of the motion, C, or D, greatest somewhere in between the top and the bottom? Greatest at the bottom of the motion, which I like as well. So my reasoning is this. As the ball goes around in a circle, it must always be accelerating towards the center of the circular path. That's that centripetal acceleration. Okay. So some combination of gravity and the tension force, are the only 2 forces in this ball, must provide the inward centripetal acceleration, or the inward centripetal force that's necessary to give it that centripetal acceleration, which is that v squared over r. So at the bottom of the motion, Gravity's acting down, tension's acting up. So basically, if there's tension and gravity, tension's acting in the right way towards the center, gravity's acting in the exact wrong way, and so you have to maximize the tension in order to counter that gravity and give it the upward v squared over r. Okay? And also probably it might be moving faster at the bottom of the circle as well. It seems to slow down as it goes up and then speed up as it goes down, right? Which sort of makes some sense. So it's another reason why tension's greatest at the bottom. Car is rolling over top of a hill at a speed v. At this instant, is the normal force greater than F? So F sub g here is, I guess, the weight, force of gravity. 50% are saying the normal force is less than the weight. And a lot of people, 36%, are saying the normal force equals the weight. So the idea here, it's kind of like standing in the elevator. Normal force is a self-adjusting force. It is whatever is needed to give you the acceleration you have. So in a lot of physics problems, you figure out the acceleration because you're told it or something like that, and then you make normal force, tension, and static friction enough to give you that acceleration. So if you're accelerating upwards, the normal force has to be more on your feet. That's why you feel heavier. Okay? If you're accelerating downwards, the normal force upward on your feet has to be a little less, so that the gravity is more and you're accelerating downward. You feel lighter. So in this case, are you accelerating? Yes, you're accelerating towards the center of circular motion. And the center of the circular path there is towards this direction. This is the r direction, I guess plus r. The center of the circular path is down. And so A sub c is down. You must be accelerating downward to stay on a hill. So you're going to feel lighter. Okay? You need your net force to be down.
If the velocity was 0, wouldn't the normal force be equal to gravity?
Yeah, if v is 0, then you get c. Normal force is equal to the weight, exactly. Because it's v squared over r. What if you're in a valley? Same sort of thing. Survey says, you got it, 92%. Me like you. Your normal force has to be greater than your, when the weight, in this case, to get you accelerating towards the center of the circular path, which in this case is above your head. Jeanette Epps is on the International Space Station, 420 kilometers above the surface of the Earth. Assuming Dr. Epps has not changed her mass since moving to space, which actually can happen because you get muscle loss from atrophying and stuff because you're in a weightless environment. But assuming that hasn't changed, how has the force of gravity, what's the new force of gravity? Is it A, 0, B, the same as the force of gravity was while she was on Earth, C, a little bit less than the force of gravity while she was on Earth, or D, not exactly 0, but much, much less than the force of gravity while she was here on Earth? Really 50-50. So drum roll, please. The answer is actually that the force of gravity is C. It's less, but not a lot less. It's only 470 kilometers up. You are right now a certain distance from the center of the Earth. It's about 6,400 kilometers. Astronaut Jeanette Epps is currently living on the International Space Station, which orbits at 420 kilometers above the surface of the Earth. That's called low Earth orbit. So how much farther away from the center of the Earth is Dr. Epps than you? Because that's going to be the r in the r squared and GMM over r squared, right? Survey says 1.07. Someone was saying she got 1.06, but it's closer than any of those other ones. Not much farther. That's like a 2-scale diagram. So I guess it would be 6370 plus 420 divided by 6370. What's going on here? A couple of questions. Why do they feel weightless is one thing. And if something's accelerating towards the Earth at 8.6 meters per second squared, then why doesn't it hit the Earth? Yeah, that's actually it. So yeah, it's B. That's the one I like. That's what orbit is. Okay, you're just moving. And so as you're accelerating down, that's actually your centripetal acceleration. It's like free fall. So, and that is exactly why you feel weightless. The idea is that if you were in an elevator here on Earth, and that elevator was accelerating downwards at 9.8 meters per second squared, then you would be in free fall. You would just be floating around the elevator as would, any object that you're holding, like a baseball or something, would float in front of you. and you would feel completely weightless, at least for a while. But when you're up in space, they turn off all the rocket boosters, okay? It becomes very, very quiet. So it actually takes a while to get up to space. It takes a few minutes. But once they get up there and park themselves in orbit, they turn off all the engines and they just float around. It's very, very peaceful. They get a great view of the Earth if they look out the window, and things are just floating. And that is because they are in free fall. Now, it's not 9.8, it's only 8.6, but they're accelerating downwards at 8.6 meters per second squared, and that forms their centripetal acceleration. In low Earth orbit, a satellite is only a few hundred kilometers above the surface. It only went up maybe 300 kilometers, something like that. So, why do they do that? It costs a lot of money. Why that distance? A, lower than that, they would be subject to Earth's gravitational pull and the satellite would fall down. B, lower than that, they would be too far from the sun and could not collect enough solar power. C, lower than that, they would be subject to too much air resistance and would fall or burn up. D, lower than that, they would be subject to too much radio interference from Earth. Or E, lower than that, they would not be able to communicate with the entire Earth at one time. That's the main reason we launch these things up to around 300 kilometers or more. So, and that is exactly it. So there's certainly a gravitational pull in space. It's just about, 10% less or something. You're getting away from the air resistance. You need to be in a vacuum in order to do this. That's the only thing. Otherwise, you would slow down and fall, okay? That's the reason that they put things into orbit.
My name is Jason Harlow, and I hope you enjoyed this video. If you have time, please fill out the feedback form on my Google Forms available in the description to this video. There's also a link to the Google Classroom where there's a public discussion forum and a place where you can ask me a lot of questions. Also available as a link in the description to this video. I look forward to hearing from you. Take care.